Hello, everyone. Thank you for coming. My name is Bob Steagall, and I'm here to give a talk to discuss some work that I've been doing with, sorry about that. I happen to have some work that I've been doing with vectorized computing using AVX 512 and AVX 2 on newer Intel architectures. And this is a two-part talk. This is the first part of that, and I call it Adventures in SIMD Thinking. So let's get started. So first of all, I'd like to do a little bit, help us learn a little bit about Intel's SIMD facilities. And a disclaimer here, I don't work for Intel. I'm not compensated for this. This is all just work that I've done on my own. We'll create some handful of useful functions in terms of the AVX 512 intrinsics, which are particularly interesting because they are 512 bit integers, which hold 64 bytes, and 16 floats or 16 32-bit ints, which is an interesting quantity. And then we'll try some SIMD style thinking to tackle some problems that I think are interesting. And we'll try to get through 4 of them here. The first is intra-register sorting. So if you've got 16 values, floats, or ints in a register, can you actually sort them? It turns out you can. We will use that to implement a fast linear median of 7 filter. And then that'll be the first talk. And then I think in the second half of the talks, we'll look into some fast small kernel convolution. So if you're convolving a linear signal and you have a kernel size that's less than 16, we'll see how to do that and do it very quickly. And then finally, I'll do a reprise of some work that I did and presented a couple of years ago where I was using SSE intrinsics, an older version of the intrinsics, to convert UTF-8 to UTF-32. And I will show a slight improvement today. It's not a huge improvement, not nearly as much as I'd hoped for, using AVX2. And on 2 out of 3 compilers, we see a decent improvement, and on the third, there's really no change. So there's not really any heavy code. There is a lot of code. There's lots of pictures. The code that's here today is all C++, but it's all very simple code. It could easily be done in C++ 14 or higher. So let's get started. These are just some fundamental definitions that are part of what we're going to use here. We really don't need much. We need facilities from C_IO, which I use for debugging. We need the standard it definitions, and we need some things out of type traits. Otherwise, we're going to include the immintrin.h header file, and when we're building in optimized mode, we're going to tell the compiler to force it to inline. Otherwise, if we're building in debug mode, we'll just use ordinary inlining. Of particular interest for this talk are these 3 types. I call them RF512, RI512, and MSK512. And these correspond to the 512-bit floating point integer type that Intel defines, the 512-bit integer type, and then the mask type that I use, which is an unsigned 32-bit int. And these 3 types really form the basis, are used by all of the functions to do the work that we're going to look at. So there are 10 to 15 different functions. Each of them are important for understanding the algorithms that are discussed later on. So I'm going to try and get through those and then see how they can be applied in some of the interesting problems that I mentioned. So we'll start from the ground up with the most basic of the algorithms, the most basic of the basic algorithms to more complex basic algorithms. So the first one is very easy, the first 2. We want to fill a register, a 512-bit register with some value. So the function is very simple. I pass in the floating point value, I call the intrinsic, and I take the floating point value, and it broadcasts, the intrinsic broadcasts the value of the argument to all of 16 elements that are part of that 512-bit register. And there is an analogous function for ints, for int32. And int32 and float are types that are natively supported by the 512-bit integers. Intel's intrinsics are often mostly written in terms of, or a large percentage of them are written in terms of 32-bit integers, 32-bit floats, doubles, 64-bit floats, and then some other types for smaller type manipulation, both at SSE and the more expensive Skylake processors, where you pay a lot more money for advanced AVX512 capabilities. But we're really only going to deal with 512-bit registers that are holding 16 values, and those values are either going to be 32-bit floats or 32-bit integers. So the next interesting function I call load from, and this is a function for loading data from memory, floating point memory from data. So if I've got a pointer to some memory and I call the function, it will load that into my register. And if you're familiar with the intrinsics, you'll notice that I am using unaligned loads and unaligned storage, or unaligned stores when I do stores, which is indicated by the U in the name. And the reason for that is because of the way the algorithms work, I really need to be able to load from any arbitrary int32 address or any arbitrary float address. The next function is I call masked load from. And this is a function that takes a pointer to some floating point data. It takes a fill value, and it takes a mask. Now, Intel actually uses 16-bit masks. I use 32, and I cast them to 16. And there's a reason for that that's unrelated to this presentation, but I kept it in the presentation. So the idea is you have a pointer to data, and you have some fill value, and you have a mask. And then when you execute the intrinsic, what happens is for every place the mask is a 0, you get a value of the fill. And every place the mask is a 1, you get the value from the corresponding location in memory. So you can see here I'm alternating in pairs of 2 because I'm alternating in pairs of 2 in the bits. And in the top half of the register, I alternate in units of 4. But everywhere you see a 0, I'm getting a value from the fill. And everywhere you see a 1, I'm getting a value from memory. This actually turns out to be pretty useful. Likewise, there's another variant of this, which is just an overload that I've done here. And that is taking, that actually specifies a different fill value for every location in the fill register. So rather than having a single floating point fill value that gets broadcast, instead, I supply my own fill values, and again, where there's a 0 in the mask, I get the fill value, and when there are 1s in the mask, I get the values read from memory. And corresponding to load from, there are functions to store to. So there's a simple function, store to, where I take a float and a register that's got data in it, and I stored that. Now, here's my memory, here's my register with values, and at the end, I've pushed all those register values from the register into memory. And just as there was a masked load from, there's also a masked store to. And so the idea is that wherever there's a 1, I think I've got it backwards on my diagram here. Wherever there's a 0, you should be getting the, wherever there's a 0, you should be getting the value of the fill of the register. And wherever there's a 1, you're getting value from memory. Yes. So anyways, same sort of thing. You see alternating with 0s, I'm getting values from memory, and with 1s, I'm getting values from the register. The next function is a constexpr function, which is pretty useful. It's very straightforward. It's all evaluated at compile time. And I call this make bit mask. And this makes 16-bit masks for me and returns them in an unsigned 32-bit integer. And the idea here is that the bit values, 0 or 1, are provided as template arguments. So it's all done at compile time. And so I have 16 template arguments, capital A through capital P. And what I do is I statically assert to make sure, because they're unsigned integers, I statically assert to make sure that their value of all of them is less than 2. So every value here, A through P, has to be either 0 or 1. And then once the static assert clears, then I just do some bit shifting and a bitwise ORing to build the bit mask. And so the bit mask would have from low order to high order, A through O. And I should also mention for this presentation, the convention for both registers and memory and also bit masks is the low order byte and the low order bit is on the left, and the high order byte or the high order bit is on the right. And if you took this representation, this register based representation of a bit mask, and you wrote it out in a big Endian form that we do traditionally, it would look something like this if you represent it as a bit sequence. The next function is blend. This is a very important function. Again, it's based on masks and allows me to take two registers, A and B, and where the mask is 0, I get values from A, and where the mask is 1, I get values from B. This is a very interesting and very powerful function. It gets used a lot in the other functions. Very straightforward. The next function is also very powerful and very useful, and I call it permute, and it's based on this intrinsic, this AVX512 intrinsic. So basically what happens is you have a register full of values, and you have a permutation sequence in another register, in an integer register. And the values at each location in the permutation sequence indicate which value you would like moved into the result. So for example, at the 0th index, I'm indicating that I want the value from the 15th index to be returned in the 0th index in the result. And so you can see that by having a permutation sequence which decreases from 15 to 0 and applying that permutation, as an example, I have reversed the order of elements in the register. And likewise, you can do the same sort of thing with masking. You can have the permutation mask, you can have the permutation register and you can have the mask. And then everywhere the mask is 0, you get the values from the original register. Everywhere the mask is 1, you get the permutations. So for example, the mask bits are 0 here, so I get R0 and R1. Here the mask bits are 1, so I'm going to get R13 and R12, which I do, and so on and so forth. So a useful thing to be able to do is to actually have a function template in this case, that makes a permutation map for you. So just like the make bitmask function, I have a function template called make perm map for make permutation map. And it also takes unsigned template arguments, 16 of them. And so what happens is you enter the function, and again, there's a static assert which validates that the value of each of these unsigned template parameters is less than 16, meaning it's from 0 to 15, and therefore is a legitimate index for permutation. And then it applies the appropriate intrinsic to actually execute that permutation. And so they'll be in the order that they are specified in template arguments. So these will be the values of the permutation mask. So we can use the permutation mask, and we can use permutation in general to actually rotate values in registers. And this is also very powerful and necessary for the algorithms we're going to discuss. So the next function I call rotate, and it takes a template parameter, a signed integer template parameter, and it will actually rotate the contents of a register left or right. First thing it does is it looks to see if the rotation value, capital R, mod 16 is 0. If that's the case, then the result is the same as the original register. If not, then the function computes a bias value, which depends on whether R is positive or R is negative. It then takes the bias value and uses it to generate the parameters that get passed to the the intrinsic that makes the permutation register, which then gets passed to the intrinsic that actually does the permutation. So for example, if I had this register with these values and my applied rotate with a template argument of +3, this is the result I would get. All of the values are shifted upward by 3, and the last 3 values on the end are brought around to the front. So you can see I've got 13, 14, and 15 now occupying the places where 0, 1, and 2 were. So this is a very useful function. And we can use that. We can actually write a couple of handy wrappers on that. We can have rotate down. And so what rotate down does is it takes a template argument, an integer, it assures it's greater than 0. And for rotating down, we take the rotation value, we make it negative, and that's what we apply rotate to. So in this case, if I'm rotating down to the left towards the least significant byte by 4 values, then the values R4 through R15 are shifted to the left by 4, and the values R0 through R3 end up at the high end. Likewise, we can do an analogous definition for rotate up. And here, if I rotate up by 3, you get the same result as if I call rotate directly with an argument of 3. Other useful functions are shift down. Shift down is actually a combination of rotating. So I'm rotating down by 3, or I'm rotating down by 4 in this example. I have another register that I've loaded with zeros, and I have a special function called shift down blend mask, which takes the amount of rotation and it computes the bit mask. That's not important here, so I didn't include it. It's very straightforward bit manipulation, so I left it out. But the point is that my fill register is loaded with zeros, so I rotate everything down by 4 in this case, and then I mask 4 zeros into the upper 4. So it's similar to what you get when you're bit shifting on a CPU register, bit shifting downward. Now, another important function built on that and built on permutations is one that's very useful in the median filter and the convolution, which I call shift down and shift up with carry. And this operates on a combination of registers, A and B. I think of them as being low and high. And so what happens is I rotate down A, I rotate down B, and then I blend them together. So I've got B, which I think of as high. I've got A, which I think of as low. I shift A down, or I rotate A down by 4 in this case. And then I take the lower 4 elements of B and I put it in the upper 4 locations of A. So it's as if A and B were contiguous, and I've shifted all of the elements 4 to the left. So you can have a shift up, which is the opposite of shift down. And you can have a shift up with carry. And here again with B, as I'm thinking of as high, and A I'm thinking of as low, everything gets shifted to the right. And the result is the result of taking high, shifting it to the right by 3 in this case, and taking the upper 3 elements from low and putting it in the bottom 3 elements of high. So again, it's a way of thinking of these two registers as if they're contiguous. And so when I shift up, I'm shifting stuff to the right towards the upper register, and then whatever would be the value in that upper register, that's the result after the shift. And the converse for shift down with carry. And finally, there's a variation of this I call in-place shift down with carry. And the only difference between that and shift down with carry is that I actually want the values in both registers to be adjusted in place. So I pass them in by reference. So what happens, again, thinking of this as low, or thinking of this as high, and thinking of this as low, I'm going to shift down B, in this case by 4. And because it's a shift, I'm going to fill the upper 4 with zeros. And the lower 4 original values of B are going to end up in the upper 4 values of A, and the bottom 4 values of A are lost. So again, it's as if I have A and B, A low and B high. I'm shifting everything to the left by 4 elements. I'm filling the top 4 elements with zeros, and I'm actually doing it in place in the registers themselves. Now, get to the math functions, there's surprisingly few math functions. There's only 3. There's fused, multiply, and add, which has basically A, B, and C registers, and it returns a value in the D register. And the value of each element in D is equal to the corresponding elements of A multiplied by B and added to C. So it's one operation that does a fused multiply and add to give you your result. And then there's comparison functions, minimum and maximum. And so minimum does what you might expect. Given 2 registers that have values in it, it returns a result where each element in the return register is the minimum of the corresponding elements in the 2 arguments. Very straightforward. Same thing for maximum, except it's the converse of minimum. You end up with the maximum values of the elements. Now here's a function that's a little more complicated, and it's very interesting. And it's a way to compare. It's the basis of sorting in the elements or within registers. And I call it, for lack of a better term and lack of imagination, I call it compare with exchange. So it's a primitive for sorting. So this function is called with values with a register called vals, which has elements in it, a permutation mask, which specifies which elements are to be compared, and a bit mask, which specifies when I compare 2 elements, which one is the maximum. So let's see how it works. So here I've ended up, we're going to just, for simplicity, we're going to compare and exchange the first 2 elements. So here are my original values. I've got it full from the register full from 15 to 0 in sorted in descending order. I've specified a permutation matrix or permutation register. And so I've said for the value in location 0, I want to compare with the value in location 1. And for the value in location 1, I want to compare with the value in location 0. And I've supplied a mask register. And the mask register tells me when I do this comparison, the one that has the 0 is going to be the location that gets the smaller of the 2 numbers. And the location that has the 1 is going to get the greater of the 2 numbers. So first thing we do is we compute the exchange. So we use our permutation and we exchange the values from the vals register that are specified in the permutation matrix. Notice here that each value in the register here just corresponds to its location. And that's just a direct permutation. There's nothing to be changed there. But in the exchange register, I've swapped the first 2 values. Okay, now I'm going to compute the minimum. So I look at vals and I look at exchange and I compute the minimum. Well, in both cases, the number 14 is the minimum. It's the minimum in this lane and it's the minimum in this lane. And it has to be the same in both lanes if you think about it. So now I've got the minimum. Likewise, I'm going to compute the maximum. I do the same thing except I look for the maximum value. And here again, between vals and exchange, the maximum is 15 in both locations. So now for these two elements in the register, I have values for the minimum and values for the maximum. Now I'm going to blend them using the bit mask. So I've got my bit mask, and my bit mask is telling me I'm blending vmin and I'm blending vmax, and my bit mask is saying for the 0s, get the value from vmin. For 1s, get the value from vmax. And lo and behold, I've just sorted the 2 values of the first 2 elements in this register. I think that's pretty cool. So why is this useful? This primitive is very useful if you want to actually sort the values in a register. I look at this, when I first looked at this and realized this could be done, and I found it in a paper I was reading on AVX intrinsics, and I thought that's really cool. You can use it for sorting. And it only took a few seconds later before I realized lots of people had already thought of that. I wasn't creating anything new, but it's still pretty cool. So how do you do the sorting? Well, these things I've learned about recently called sorting networks, and you can look them up on Wikipedia, and there are sites that will generate optimal sorting networks for you. But what it boils down to is each one of these lines, these horizontal black lines, represents, in effect, a wire. And these were actually used physically in electronics in the late 60s to do sorting in electronics. It's amazing. But each one of these represents a lane, and each time you see a crossbar, this represents a comparison. And, you know, you can actually do, across the lanes, you can do multiple comparisons in parallel. So each set in this diagram where you have groups where all of the elements are engaged, because it's a power of 2 in this case, is one phase in the sort. So I'm going to sort every adjacent element, then I'm going to do this style sorting, sort every adjacent element, then I'm going to do sorting according to this pattern, according to this pattern, and then finally flip every adjacent element. And this is called a botonic merge sort, if I'm using the terminology correctly. And in this particular case, it has 16 inputs, and it will sort them into 2 sorted lanes of 8. And it's the same number of operations no matter how the data is sorted. If the data is pre-sorted, it still works. If the data is inverse order, same number of steps. Random order, same steps. Very powerful and cool idea, and directly applicable, because if you think about it, each one of those lanes corresponds to one of the elements in our 16 element register. So, as it turns out, for those 6 steps, you can pre-compute the permutations and the bit masks necessary to carry out the operations that you saw in that diagram. And I'm just going to turn it sideways and sort of blur the rest. But you can see that in this first step, I'm doing a permutation for each adjacent pair of elements. And my bit mask has a 0 on the left and a 1 on the right, meaning that I'm keeping the lower number on the left and the higher number on the right. And this will do the first phase of this sorting. And it does it in one pass through compare exchange. So there are 6 passes through compare exchange, and each compare exchange takes, if I counted correctly, 4 intrinsics. So 24 intrinsics calls is enough to support 16 elements in 2 lanes of 8. So here's the rest of the function after I've pre-computed the permutations and the bit masks. So I start with my vowels. I'm going to do my first compare exchange, and you'll see that it's worked. I've got adjacent pairs of elements have been reversed. My second permutation, and well, I can't remember which ones are which, but as you step through, and I've left the last 2 in each case unfuzzed so that you can look and see the difference. As you step through, the sort progresses. And then by the time you get to the end, you have a sorted sequence. I started with 16 through 1, and I sorted 2 lanes of 8. So my lower lane, I have 9 through 16, and my upper lane, I have 1 through 8. So I think that is incredibly cool and very powerful. So now that we have this ability to do sorting inside a register, how can we actually apply this in the real world and get something useful out of it? Well, I was several months ago, about a year ago, tinkering around with some audio signal processing. I had a noisy signal, and audio signals are just linear signals, and I wanted to just fool around, try some denoising. And so one of the things that I saw suggested was the idea of a median filter. So stepping back for just a moment, let's think about how you compute the median. The median is the central of some set of sorted values, such that half the values are on the left and half the values on the right, or equal number of values below and equal number of values above. So one of the things I wanted to do was try a median filter that had 7 elements in it. So for each element, or each point in the signal, I would take the point in the signal, compute the median of that and 3 points previous and 3 points after, and see if I could remove noise. Well, with a fast sort, we could implement a median of 7 linear filter pretty easily. So as I said, a median is a value in a set of sorted data where half the values are less than the median and half the values are above the median. And if you have an odd number, then, which is usually preferable, then you have equal numbers below and equal numbers above. And keep in mind, if you have an array A of 7 integers, and these are the sorted integers that you want to compute your median from, assuming that you're indexing from 0 to 6, the median is going to be in index 3. So keep that in mind as we go. So median filters are useful because they're good at preserving edge features in a signal. And if you have a large discontinuity, it's good at preserving large discontinuities because typically if you have areas in your signal where you have a shelf, typically the median will actually preserve the shelf in the signal. If you have a lot of outliers, though, a lot of noise, it's good at getting rid of them without actually blurring the signal. And as I mentioned, it's good for denoising. On the right here is just a diagram I cribbed from the internet showing an example of an original signal that is a little bit noisy, and then having applied a median of 7 filter to it, you can see that a lot of the characteristics of the original signal are preserved, but it's a little less noisy. And that was the effect that I was trying to achieve. Unfortunately, I didn't have any success doing that. On the left, you can also do median filtering in 2-dimension. And so this is an example of the famous photograph of Lena. And here you've got some added speckle noise to the photograph, and a 2-dimensional median filter has been applied to the photograph. And you can see that it removed a lot of the noise without really damaging too much of the edge detail in the original picture. And I'm not sure whether the median filter here was a 3x3 or a 5x5 or 7x7. I'm guessing it's probably probably a 5x5. But in any event, that's what median filters are good for, preserving strong characteristics while getting rid of noise. So how can we do this? Well, I'm going to walk through some code for a function that I call AVX median of 7. And this is a little bit tricky. There's a lot of code here. I've interspersed the code with some diagrams in the hopes that the diagrams will help illustrate what the code is doing. The function starts out by pre-declaring several float registers, 16-element AVX 512 registers. And there's previous, current, and next. And these are registers which represent the data input window. These registers will actually hold the data which I'm reading from memory. And as their names might suggest, the current register is the one that contains most of the data that I'm currently processing. The previous register contains the data that came before, and the next register contains the data that came after. Now you may be wondering, why do I need to keep the registers on each side? Well, you'll see when we get to the pictures that when you're starting the processing, you have boundary conditions that you have to worry about. So you need to decide what to do when you're computing the median, applying the median filter to the very first element in your array. There are no elements before it, so you have to pretend there are elements, and that's, in a sense, what the role of the previous register is. It fills in for memory that's not actually there. Then we have work registers, low and high, and you'll see what their role is. It's easier to see pictorially. You have a data register, which holds the result of computations, and you have an accumulator register, which holds the results of computing the median as we go. So we talked about loading data into lanes. And so here's the permutation that I use here. And look carefully at the permutation. So the first 8 elements are ordered 0 through 7, as you might expect. The second 8 elements are ordered 1 through 8. So effectively, my lower lane is going to sort elements 0 through 6, and my upper lane is going to sort elements 1 through 7 inclusive. And so we make a permutation register, which we'll apply later to extract data from another register in that order so we can do the sorts. There's another permutation map that I call the save permutation. And you'll see that it's full of these weird numbers, 3 and 11. And the significance of those numbers will become clear when we actually see an example in the diagrams. But keep in mind, they're pairs, 3 and 11. So I begin execution. First thing I'm going to do is I have a work register called first, and I'm just going to load it with the value that's in the 0th element in my array. And first is going to temporarily hold this data for purposes of the lower end boundary condition. I'm going to compute my permutation, and I'm going to compute my save permutation. Now keep in mind, actually, these things are declared consts, and there's no work here that's done at runtime. The compiler actually pre-computes these things ahead of time and puts them in static memory. The next thing I do, and I'm jumping down a little bit here, is just scrolling down in the code. I create a bit mask using my make bit mask function, and that bit mask has the lower 2 bits set to 1 and 1, and all the other bits are 0. And so now what I'm going to do is I'm going to make an array of such masks, and I'm going to, for each element in that array, I'm going to take my original mask and I'm going to shift it by some value. The 0th element is going to be shifted by 0 bits. The first element is going to be shifted by 2, and so on and so forth until the 8th element in the array is shifted up by 14 bits. Okay, now I'm going to preload some data into my registers. So I've got my preloaded data first. I'm going to load that into my current register, and I'm going to read the first set of data from source, and I'm going to load it into next. So this is what it looks like, and hopefully these pictures will make sense. I've got cur, and cur has my, I've broadcast the values of everything that's right here into it, and next, at the beginning of next, contains the beginning of my data. Now I'm going to go into the loop that actually does the work. And the first thing that I'm going to do in the loop is I'm going to read another register's worth of data, and I'm going to shift everything down by 1 register worth. So cur becomes previous, next becomes cur, and I load more data into next. So now I get this. I've shifted what was in cur down to previous, what was in next to cur, and I've read new data. So this is original fill data. This is my first element that I've read, and my data goes off to the right. Now, this is where I'm going to use this weird function I mentioned before, shift up with carry. This is where it gets useful. So my low work register, I'm going to shift up by 3 elements because my kernel, my median filter, has 7 elements in it. I want to do a median of 7. So 7 divided by 2, integer addition is 3. So I have to shift, I'm going to shift previous and current up by 3 locations, and I'm going to store the result in low. So let's see what that looks like. So in effect, what I've done is I've taken previous and cur, and I've moved it to the right by 3. And this is how I've loaded the initial values of low. So low and high, and high does the same thing except for cur and next. Low and high are shifted to the left by 3 elements relative to cur and next. And that's because when I want to compute the median for this element, I need to be able to access these elements here. So, all right, so now I've shifted, I'm ready to do some work. So in my work register, I'm going to use my load permutation that I mentioned before, and I'm going to take the data in low, I'm going to permute it, and I'm going to put that in work. So here's what that looks like. I've got low, I'm taking the first 7 elements of low and loading them into the first 7 elements of work. I'm leaving the 8th element blank. I'm taking the next 7 elements of low, elements 1 through 8, and I'm loading them into elements 8 through 14 in work. So I've loaded my 2 lanes with the first 7 and the second 7 elements from my data. Now I'm going to sort my lanes of data. And I didn't show you sort 2 lanes of 7. I thought 2 lanes of 8 was enough, and the diagram of 8 is actually easier to understand than the one of 7. But it executes in the same time. It takes 6 steps. So I'll just hope that you'll trust me that it works. So I sort the data, and I've sorted the data now. That's what the blue is intended to represent. And because I have 7 locations, here's my median for my first lane, and here's the median for my second lane. And guess what indexes these are? This is index 3, and this is index 11. So now I'm going to use my save permutation, and I'm going to use the save mask, those weird things that I computed before, and I'm going to use them to place my results, the 2 medians, into the register called data, which is an accumulator. So here you go. I've taken 3 and 11, and I've put it into the first 2 locations in the data register, in the accumulator. So I've essentially taken a lane of 7 and a lane of 7, or the first 7 elements, the second 7 elements. I've sorted them in 2 lanes. I found the median for those 2 sets of 7, and I've put them in the first 2 locations of my accumulator. I go back, and this is where the shift down with carry is in place, because I want to preserve the values in low and high, but I need to shift them. And I didn't want to have to return a tuple, so I used references instead of returning by value. So what happens when I do that shift is I effectively am shifting the values down, or relative to cur and next, I'm shifting low and high upward. So you'll notice that the values in low have all gone to the left by 2. The values in high have gone to the left by 2. And at the upper end of high, because it's a shift, I filled it with zeros. Now I repeat the process again. I take what was the 3rd lane of 7 and the 4th lane of 7. I load them into my work register. I sort them, and I use my save mask. I use my second save mask bit mask, and now I've saved the 3rd and 4th median values into my accumulator. And I'll do that 4 more times in order to fill the rest of the data register. When the data register is full, then I will write that out to memory somewhere, and I'm done. So, all right, so I've made this claim that it works, and I've made the claim that it's fast. So how fast is it? Well, let's take a look. I wrote some code. I wrote this code. So because I'm using AVX512 registers, I had to use something higher than Knight's Landing, and not having that, I had access to some Skylake and Cascade Lake machines. So I used a Cascade Lake machine to build this. So it's done on Ubuntu 18.04 on a Xeon processor that's Cascade Lake, and I'm not sure what series it is. It's 2 gigahertz processor, 6200 something. I don't know what exactly. And I built the code with GCC 10.2 and Clang 10.01 just for purposes of comparison. And here are the flags that I used when I was doing the building. To test how fast the sort was, I used element counts of 100 through 10 million, increasing by a factor of 10 each time. So there's basically six tests. And I tested the data with pre-sorted integers where the integers increase monotonically. And I also tested with randomly generated signed integers whose values ranged from -50 to +50. And this range doesn't mean anything, except when I was printing out for debugging, I wanted the amount of space for each integer to take no more than 3 characters and be easy to recognize. So I used -50 to +50. As part of the test, if you look closely at the test program, I'm always using the same seed to generate the data. Now I'm using a Mersenne twister with a number that I found and used to generate the twister. I don't care about the random quality of the data. I just want it to be random enough to determine if there's a difference between pre-sorted and randomly generated input data. And always generating from the same seed allows me to compare apples and apples run after run. So I used 2 approaches. The first was I took the same idea and I wrote a program that uses STL stood sort, and that program scans along the input array and creates a short work array of 7 elements, uses std sort to find the median, and takes the median and puts it in the destination array. I also used the small kernel AVX512 sort that I just showed you. And I went to great pains to make sure that both for the monotonically increasing data and also the randomly generated data, that I always got exactly the same result in every location from both sorts. So let's look at sorted input. So here I'm using a log graph, right? So these are factors of 10 and factors of 10 in the size. So this is the execution time in nanoseconds, because sorting 100 really only takes not very many nanoseconds. In nanoseconds for the STL sort and for the AVX sort. And I'm actually pleased at how linear this relationship is on this log-log graph. What it's saying is if I increase the number of elements by 10 times, then the time that I take is going to increase by some constant factor. And the lines have almost identical slopes, and they are a fixed distance apart. And so you can see I also computed the relative speed up. How many times faster was AVX than STL in this case? And it was basically, in the case where the data is sorted with GCC and using GCC's libstd++, the AVX-based approach for pre-sorted data was always about a factor of 4. So you get a nice constant number there, and that explains the parallel lines that are equidistant on the graph. When I went to random input, the performance and the time that the AVX sort took was no different, almost no different, within the noise for the random input or for the pre-sorted input. And as I mentioned, for every sequence in the step, exactly the same number of sort operations need to be done by compare with exchange. Whereas you can see there was a little bit of change in the slope here for the STL algorithm, std sort. And you'll also notice that the performance difference bumped up and became asymptotically around 18 or 19 times faster. So in this case, because the data was random, std sort actually had to do work. It had to do comparisons. It had to swap elements. In the pre-sorted case, the amount of work it has to do is much less, which is why it's much faster. So you get a nice relative speed up there relative to random input data, which I would think more or less corresponds to the real world, but who knows. So with Clang was interesting. With Clang, the performance difference between AVX and STL was much tighter. And interestingly enough, on the same platform, Clang was actually creating faster code with libstd C++ than GCC was in terms of absolute execution times. So the factor difference here sort of asymptotically was around 2. Still nothing to sneeze at, and I think that's pretty good speed up in this case. For random input, the difference in performance spreads out a little bit again. It's closer for small numbers, and then it gets not quite as far apart as it was for GCC, but you can see asymptotically for 10,000 elements or more, the AVX-based sort with random data is around 16 times faster than using std sort in libstd C++. Now, I'm cognizant of the fact that std sort is probably not the way that really smart people that know what they're doing would do this. And I expect that it's probably, it's a very good sort, but it's also worst case performance probably for somebody who's doing this kind of processing for real. I don't really do that for real, and I needed something to compare against as a baseline. And so I chose to use std sort. So that's it for this half of the talk. Thanks for coming, and I hope you'll come back to the second half. I've got a few minutes left, so I'm going to move over to Remo and answer some questions in the Q&A. Okay, so the first question is, now that Apple is moving away from Intel chips, what will the future of SIMD development look like in cross-platform products? Well, if I had a crystal ball, I would keep the answer to myself and make a lot of money from that. So I don't know. I will say that I don't really have a good feeling for how Intel SIMD compares to other SIMD chips. I would like to compare absolute and relative speedups on other chips like ARM or MIPS or other things. And I would have done that, but I don't have access to that kind of hardware. You know, in my world, I am surrounded by Intel, and there's really Intel and NVIDIA, and there's really nothing else. If somebody wants to send me some free hardware, I'll happily take it and do some benchmarking on that as well. The next question is, wouldn't STUD nth element be enough to find the median as a baseline rather than the full STUD sort? It may be, I don't know. I didn't think of that. Now that someone has brought it to my attention, I think I have a third, if it works, I have a third baseline case that I can add to the processing and see how it compares. I think it would, but I'm not absolutely sure. And the last question that I see is it possible to use constexpr to perform complex register initialization? And the answer is not yet. constexpr, the compiler, it would have to be a compiler-specific extension. The abstract machine doesn't recognize registers. It doesn't recognize these special constructs in C++20 or earlier. So there is no way to make it constexpr. Now, I found, from a practical perspective, even in debug mode, when I declare those register structs to be const, the compiler still puts them in static data storage and actually doesn't do any work at runtime. It preforms them. My understanding is in the committee that there are people looking at how we can actually take intrinsics, whether they're Intel intrinsics or from other companies, and extend the abstract machine and the language in such a way that those things can be accommodated by constexpr. Okay, so the next question is there a relevant performance difference between aligned and unaligned loads on recent hardware? Well, I think there are. Well, so here's measurements that I've done informally, and this is purely anecdata, so don't take it seriously. In some of the algorithm work that I've done at work, I built an aligned allocator where allocations were always aligned on a 64-byte boundary, so that I could start at the beginning of the array and I could read data into registers in a 64-byte chunk. And in the tests that I was doing, after reading data, loading the data from memory into registers and doing work on them, and timing that, and there was quite a bit of work. So I tried it with both aligned loads and unaligned loads, and I couldn't see any difference in that case. When the data was aligned, there didn't appear to be a whole lot of difference between load U and regular load. I did find, to my chagrin, when I had unaligned data, like having to start the address, load a register from some arbitrary float register or some arbitrary float location in memory that you can't use, you'll get a segv if you use load aligned. Found that very quickly. So now I just default to using unaligned loads and stores for everything, and for the cases where the loads and stores are actually aligned, there doesn't seem to be any performance difference. In the case where they're unaligned, I can't compare it to the aligned loads because I get segvs. There's another question. Are the AVX2 SIMD instructions rather similar to the AVX512, or are there bigger differences than the width of the registers? Well, certainly AVX512 is twice as large as AVX and AVX2. And AVX and AVX2 are twice as large as the original SSE intrinsics, which are twice as large as the MMX intrinsics. So who knows if it keeps going. So there's quite a bit of new functionality that's in AVX512 that doesn't exist in AVX2. I think that everything that I've shown so far could also be implemented at half the width in AVX2. I've just not done that yet. But there is some very cool things in AVX512. There's gather scatter primitives. Now, AVX2 has a gather primitive, but it's basically just a full register. I don't remember if it has a masked gather or not. But AVX512 has gather scatter, and it has masked gather and masked scatter. It also has compressed load. It also has compressed load and compressed store. So if you have 16 floats in a register, and you have a mask, and you need to specify, I only want to write 11 of those to memory, with a masked store, it will only write 11 and leave the other 5 alone. So, and there are some other capability difference. If you want to pay lots of money for the super high-end AVX processors, they include primitives at those levels of processor to allow you to work with individual bytes and 2-byte segments of the register. But those processors are quite expensive and not where I work, and certainly out of reach of my budget. All right, well, I think that's it for this segment. Thank you, everyone, for coming. If you're interested, please come back in half an hour for the second half, and hopefully I'll see you there. Thank you. Take care.